All right, so now that we know how to perform function combinations, or that is to say, add, subtract, multiply, and divide functions, let's take a moment to look at what these function combination graphs would look like. So take a moment if you'd like to pause the video here and sketch these graphs out, or just follow along and visually see what's happening here as we add these two functions together. So f plus g of x, what this is saying is f of x plus g of x. And probably the easiest approach when it comes to just doing addition or subtraction of functions and trying to graph that result is to remember that the outputs of the functions can simply be added. That is to say, I can say that f of 0 plus g of 0, for example, is going to be equal to f plus g at 0. So what this looks like here is really simply when x is equal to 0, I can just go ahead and add -1 plus 2. And what is -1 plus 2? That's just going to be equal to +1. And I'm going to place a point there. Okay? And just continue on with the integer values that we see here. So what is 3 plus 1 when x is equal to, or 3 plus 0, excuse me, when x is equal to 1? Well, that's equal to 3. When x is equal to 2, 1 plus, this would looks like it's 1/2 would be 3/2, so right around here. And then when x is equal to 3, 2 plus 0 would be equal to 2. So this graph would look something like this. Okay, and I think I did all that right. Let's see, 2 plus -1 is 1, 3 plus 0 is 3, 1 plus 1/2 is 3/2, and 2 plus 0 is 2. Great, that looks good. All right. Let's try now doing f minus g of x. F minus g of x. And again, what this means is f of x minus g of x. So we're just going to do the same process, but this time we're going to be subtracting our outputs. So hopefully it's not too much for me to scrap this on here. So I'm just going to erase these so I have kind of a blank canvas to work from. Let's get this out of the way. All right, so now let's do f of x minus g of x. Well, again, this time all we're going to do is we're going to subtract. Now, the order of the values that we're subtracting absolutely matters here because subtraction is not commutative. So 2 minus -1. 2 minus -1 would give you +3. On the next point, 3 minus 0 is just 3. 1 minus 1/2 would give you +1/2. And 2 minus 0 would give you +2. So if I connect these dots here, I would get something that looks like this. Okay, so adding and subtracting function combinations is actually pretty doable as long as we can just remember we can add and subtract all the outputs. Now, how can we be sure that what's happening in between these integers is just going to be linear? Well, the functions themselves are linear here, so we should get linear outputs. But that is a great question to ask yourself because you might be wondering, well, what do we do when the functions themselves may not always be linear or they don't result in a linear output? So let's take a look at an example like that. Let's try this next one here. Okay, so let's take a look at this example here, and I'm going to go back to, well, let's switch to purple. Okay, so instead of doing f plus g of x, let me actually wipe this out. Instead of doing f plus g of x, let's try, let's see here, let's try doing f times g of x, which again, this is equivalent to f of x times g of x. So what we're going to do here is we're going to actually multiply our outputs. So we're going to do the easy part first, which is just to multiply the outputs. So when x is equal to -2, +2 times +1, well, that's just +2. So go through and multiply these outputs. 1 times 0 is 0. When x is equal to 0, 0 times -1 is just 0. 2 times -1 is -2. And 2 times 1 is +2. Now, don't just jump into right away connecting the dots just yet. You have to look at the degree or nature of the function as you go along. So consider for a second just what's happening here from -2 to +1. Let's just look at this interval here from -2 to -1. Let's just look at what's happening there. Ask yourself, what is the degree of f? Well, the degree of f looks like it's going to be 1. That is to say, f is linear there. Specifically, can you actually just look at that piece of the function and see what f is? Well, f looks like it has a slope of -2. So it looks like the function here is f of x is equal to -2x. Now, it technically does appear like it has a y-intercept of -2, and if we wanted to do that, we could. It's not really going to change what we're looking for here. But f of x from -2 to -1, right? So we could say here from -2 to -1 when x is between -2 and -1 appears to be -2x minus 2. Okay, and again, you don't have to go this detailed here. I'm just trying to make a point. Not a physical point, but you'll see. All right, now for this function here, probably actually clean this up. If I'm going to do this, might as well do this right. F of x is equal to following. Now, what about g of x? Well, g of x here, actually don't need that brace at all. G of x between -2 and -1 would be what? Well, g of x just looks like it's a constant of 1 when x is between -2 and -1. So ask yourself, if we're doing f of x times g of x here, what is -2x minus 2 times +1? Well, anything times 1 is itself. So the function here is going to be exactly the same as what f of x was. It's going to behave as -2x minus 2 because we're multiplying a linear by a constant. All right? Now let's switch colors just so I can model the next part here. What about from -1 to 0? So let's just do this here. From -1 to 0. I'm going to get that out of the way so you know which part we're looking at. Now from -1 to 0, what is f of x? From -1 to 0, f of x looks like it would just be -x. What about g of x from -1 to 0? How does g of x behave? Well, that looks like, oh, I apologize. F of x was -x minus 1 technically. G of x here looks like it's going from it's just defined as -x. Well, if we multiply these together, what does f times g of x look like? This would be -x times -x minus 1, which is just simply x squared plus x. Well, this may be a little tricky for people to graph right now, but the key idea here is that we have to understand that this is a quadratic function. That, in other words, from -1 to 0, the result of multiplying f and g is going to be quadratic. In other words, it's going to be a parabola. Now, how far down do we have to go? This is where you may just want to plug in something like, let's say, -1/2 into this function. So we would say -1/2 squared is 1/4 plus -1/2, which is just -1/4. So when x is equal to -1/2, our output is going to go down to -1/4. Oops. Right around, let's say here. So it's going to parabola that looks like this. Okay, so the key idea here is to understand that when we're multiplying a linear function by another linear function, our result is quadratic. Therefore, we should have a parabola. So the rest of it hopefully is a little bit easier. What about when we go from 0 to 1? As we go from 0 to 1, we're multiplying a linear by a constant. So a linear by a constant, which would mean that our result is going to be linear. We get something that looks like that. We don't have to really even always write out what exactly the function is. We just need to know the degree of the function within that interval. Between 1 and +2, again, we have a linear function. F is linear there. G is a constant. So linear times a constant, our degree remains 1. It's just going to be linear. And let me just make that a little bit more clear. Okay, and might as well just keep everything blue just so we can see there. That's what our resulting graph should look like. And I'll clear this out of the way just so we can see. Okay? Finally, let's talk about what happens when we divide. So let's try this last example here with division. So move down here. Okay? And this time, again, instead of doing f plus g of x, let's do f divided by g of x. So f, let's go f divided by g of x. Okay? So remembering here, f and g, right, looks like they change positions. F is then increasing or greater than g at some points and less than g at some other points. So just keep track of that. So first off, let's do the division of the outputs. Those will be kind of our benchmarks or guides for our graph. So f divided by g. So remember, f is the lower point here at -2. So 2 divided by 4, I'm going to get 1/2. Okay? When x is equal to, well, I guess we could even do this part here. At -1, it looks like f is 1, and g is going to be 3, so then that would give me 1/3, so right around there. At 0, f is 0 and g is 2, so that's just going to give me 0. At +1, f and g are both 1, so 1 divided by 1 is 1. At x is equal to 2, and this is an important point I want to make here, f is 2 and g is 0. Well, 2 over 0, that's undefined. And graphically, how does it look when something is undefined, when our function is undefined? Well, that means we're going to have a vertical asymptote here at x is equal to 2. It is undefined there, okay? And that's definitely going to affect our graph. Let's finish this off. At x is equal to 3, 3 divided by 1 is 3. At x is equal to 4, 4 divided by 2 is 2. And so we've got all of our outputs. Now, let's go through the intervals here. From -2 until 0, from -2 until 0 on the x-axis, so in this interval here, I am dividing a linear function by another linear function. Well, linear function divided by a linear function, well, specifically, if I wanted to write it out, between -2 and 0, f looks like it's, what is that? Looks like it's -x. G looks like it would be -x plus 2. So if I'm dividing f and g, f over g of x in this interval is -x over -x plus 2, which you can also write as +x over x minus 2. Do we need to get that specific right now? No, but we do need to understand that it's rational, which means this graph is not going to be linear and it's going to be somewhat curved here, okay? Now look at what's happening between 0 and +2. Between 0 and +2, I've got a linear function divided by another linear function. Again, that would make this the resulting quotient is a rational function. So it's going to be somewhat curved. And this asymptote is key for us because it tells us that our function is going to start approaching positive infinity. It's going to increase without bound there towards that positive infinity because it's a rational function here. Specifically, this would be x over -x plus 2. Okay? And then what about after that? Again, we have another linear function divided by another linear function. Kind of get the drill by now. Again, it's going to be a rational function here, increasing without bound. Okay? So really just considering the degree of the function and how that affects your resulting combination is what's key. All right, so hopefully that helps break down how we might graph combinations of functions.